Welcome to another mathematical meditation. I'm your host, Ted Z, and today we're going to talk about Lagrange's identity. Suppose I have n real numbers, a1 to an, so these are real, and let's say I have another set of n real numbers, like so. Well, with these two sets of real numbers, I have the following pretty amazing and formidable Lagrange's identity. Here it is. And this looks pretty scary, especially this bit here. You think to yourself, well, what's really going on here? It's too complicated to understand, but I'll show you a way to kind of visualize this that will make it really, really easy for you. You'll see. Well, at first, we don't even know what's going on here, so let's try it for various n. We'll try it for n is 1. So when n is 1, we only have a1 and b1, and we can just call them a and b, dispense with the subscripts. So the first term here is just a times b all squared. Now this term here, it's not possible to do I less than j because they're both 1, so I have to say this is 0. And this term here on the right hand side, that's a squared times b squared. So is this true? Yes, it's true. So it works. Yes, it works. Now let's try n is 2, a1, a2. We have two of those. We have two b's, b1 and b2. All right. So the first term here works out to this, a1, b1 plus a2, b2 all squared. And the second term, what's that? Well, that has to be a1, b2 minus a2, b1. There's no other way to have I less than j. It's got to be 1 less than 2. No other possibilities. And we want to know if this is equal to the right-hand side. And the right-hand side is a1 squared plus a2 squared times b1 squared plus b2 squared. That's a bit of an expansion of this. But you know what? This is a very fun calculation, and I'm going to leave it as an exercise. You show that the left-hand side here equals the right-hand side. Very interesting and fun to do. So it is true for n is 2, but how do we prove that it's true for any n? I'm going to do that by considering two interesting expressions. We're going to look at them separately and see what they have in common. The first expression that I'm interested in is this. We're going to take this sum, kind of like a diagonal sum, a1, b1, a2, b2, all of the same indices, and we're going to square this, okay? So I can write it like this, and let me put a nice box around it. So this is going to be one of these expressions that I'm interested in. And the second one is like so. So it's this product. Now, notice the similarity here. When I expand this out, I'm going to have, combinations of squares of a and b. And the same here in the second object that I'm interested in. If I multiply all of this out, I'm going to get products of the squares of a times squares of b. So they're actually quite similar, but not the same. So the question is, in what way are they similar and in what way are they different? And that question, well, the answer to that question is going to give us a proof of Lagrange's identity. Okay, so we're going to study this and this. This is the first object I want to study, and I can write it like this. Like so. Okay, so in all, we'll have n by n terms when I expand everything. And I can organize these terms. For example, I can do this times this, then this times this, and so on and so on. And I can organize everything into a nice, neat square array. So let me do that. First, a1, b1 times a1, b1, and then we'll do a1, b1 times a2, b2 like this. a1, b1, a2, b2, and we can keep going until a1, b1, an, bn. The next row begins with a2, b2, a1, b1, and then a2, B2, A2, B2. And we keep going until A2, B2, AN, BN. Okay, and we can now continue down to the last one. And I'll just write that out like this. That's the nth row. Okay, so we have this diagonal here, and I will give it a special name. I'll call it the blue diagonal. So this blue diagonal is like super important, right? And then we have these upper and lower triangular parts of this array. So that's upper, and let's use a different color for lower. Hang on, red. This is my lower triangular part. Okay, very nice. Now notice that it's symmetrical. See, this is the same as this. It's just the other way around. And also this is the same as this, just backwards. So I can pretty easily come up with a formula for the upper and lower triangular parts of this array. So the upper one, this is the sum over the i's that are smaller than j, ai, bi, aj, bj, and you could see that here. 2 is less than n. Okay, so let's now take the lower triangular part and figure out a formula for that. There, and it turns out this one's easy to do also. Okay, but they're equal, and so I can write the sum of both upper plus lower as the following, like this. And I rearranged the a's, the indices of the a's and b's a bit. It doesn't matter. I just switched them around because this is more convenient for me later on. So I have now this expression for upper and lower. So I can now solve for the blue diagonal. So we're going to solve for the blue diagonal. That's the entire array minus the upper and lower parts. So this here is the blue diagonal, and I can now take my entire array. My entire array was this, and now I subtract off this here, the upper lower parts, and I get this expression here, which is really nice. Okay, and you're starting to see maybe some inklings of Lagrange's theorem, Lagrange's identity, because you're seeing here already I less than j, that strange bit in Lagrange's identity. Okay, this is a very important formula. Let us not forget this. We need to use it again. And now let's look at the other object that I thought was really interesting. And this was my other object of interest. I can partly expand it like this, and multiplying all these things out, this times this, and then this times this, and so on, is going to give me n by n terms. So I can also arrange this nice and neatly in an n by n array of terms. So let me do that. That's the first one. Okay, so now let's do this times this one. Okay, and so on until a1 squared b n squared, and then the next row a2 squared b1 squared a2 squared b2 squared, and so on until a2 squared b n squared. Okay, and I'll fill the rest in. an squared b1 squared, an squared b2 squared, all the way up to an squared bn squared. Okay, now look at this, look at this. This is the same blue diagonal that we had before. That's very interesting. Okay, let's apply the same procedure. Let's solve for the blue diagonal. Well, the first thing we need to do is look at this upper triangular part, and you'll notice now that with this array it's not symmetrical, so it's a little bit more complicated. I have to look at two separate expressions for upper and lower. Well, it's easy enough to write that out. It's for all the i's less than j, it's ai times bj, like this. Squared and squared. Okay, and this one here too is quite easy to do. All I have to do is reverse the I and j, because you see now the j is the big one, so you see n is bigger than 1, and so on. Right, that's all very nice, and what I can do now is find an expression for the blue diagonal. So let's solve for the blue diagonal. This is my blue diagonal here. Okay, let me use blue over here. And this is the entire array minus the upper and lower stuff. So this was my entire array. Now let me subtract off the upper upper array, upper triangular array, like so. And now let's subtract off the lower one. All right, I have this amazing expression. Let's highlight this. This is like the thing I had before, my previous expression for the blue diagonal. The question that should come to your mind is the following. What will happen if I make those two expressions equal? Because the blue diagonals in both cases are equal. Well, that's what we're going to do in the next part. We know that those diagonals of those two arrays are equal. So let's make those expressions equal and see what that gives us. Recall that this was the diagonal, the blue diagonal of the first array. Yeah, and this has to be equal to the diagonal of the second array, which, if you recall, was this. And they're both the same because they are the blue diagonal. All right, what do we do here? Well, let's take these terms, this and all of this, and bring it all to the left-hand side and reorganize this. So in fact, I can collect all the red stuff into one sum of I less than j, like this. All right, then let's finish off the right-hand side, like so. But this expression here can be factored. It's just the square of two terms. There, you see this factors this way. And there we have it. This is our beautiful Lagrange's identity. And I know what you're thinking. You're thinking, well, what possible use could this have? So in the next part, I'll show you a pretty important application of this. Let's use the Lagrange identity to prove the Cauchy-Schwarz inequality. So let's say I have all these real numbers, ai and bi, okay, like before. And the Cauchy-Schwarz inequality says this, okay, and this is usually proved, in books on functional analysis and so on, using inner products. So they prove it in a more general case for an inner product space. So if A and B are elements of an inner product space, you can write the Cauchy-Schwarz identity like this. And if your inner product is just the dot product of two vectors because your inner product spaces are n, well, then we get back this exact same identity. So we want to actually prove this directly. We don't want to use properties of an inner product. I'm sure you've seen this proof. People take a lambda a plus b inner product with lambda a plus b, and of course this has to be greater than or equal to 0, and so on. And this gives you Cauchy-Schwarz after some really beautiful tricks. This gives you Cauchy-Schwarz inequality. But I don't want to do that. Is there a way to prove this directly? And the answer is yes, we can prove it using Lagrange identity. Right, so let's see how to do that. So let's start with Lagrange's identity, and let's rearrange things. I'm going to keep this on the left-hand side and move everything else over. There, I just moved this term over to the other side. Now, the thing to notice about this is that this has to be positive or 0. So it's non-negative because this is a square. And so therefore, all of this has to be non-negative also. And so we must have that this expression is non-negative. It's interesting that it's this funny summation that allowed us to make this conclusion. That's interesting. All right, so let me rearrange this a little bit. And I get this, and this is the Cauchy-Schwarz identity, which I can also write in the following way. There, I just took the root. And now I can write it over the space Rn using a vector. So A dot B like this, and I take the absolute value. That has to be less than or equal to the norm of vector A times the norm of vector B. Very interesting. Perhaps in another video I'll get into what exactly Cauchy-Schwarz inequality is trying to tell us. But we did it. We proved Cauchy-Schwarz, at least over Rn, using Lagrange's identity, and we did it really directly without appealing to any sort of fancy knowledge about inner products and so on. Well, I hope you liked today's video. Lagrange's identity sometimes is useful in math competitions, so you should know it. And this technique of arranging sums into squares and looking at diagonals, well, I've used that before to solve all kinds of other problems. So maybe it's a technique that you can use too when faced with some peculiar algebra problem or identity. Well, I will see you next time with more mathematical meditations.